Yes. Welcome everyone to the AI for Net Zero webinar series. The webinar series is designed to bring together experts, innovators, and enthusiasts from both artificial intelligence and sustainability domains. With an overreaching goal to accelerate progress towards net zero targets, the series aims to engage and inform communities about the groundbreaking research and developments at the intersection of AI and sustainability. The webinar series will delve into the diverse applications of artificial intelligence across various domains, crucial to achieving net zero objectives like the energy, transport, environment, agriculture, and food systems. Today, we have a fantastic lineup of two brilliant speakers sharing their cutting edge research today. So, please join us in welcoming them, each with 15 minutes for their presentation, followed by a 10-minute question and answer sessions via the chat function at any time. So, our first speaker is Craig Boer. So, Craig is former soldier serving in the Royal Corps of Signals and a former A-level mathematics lecturer. Craig received his degree in mathematics in 2004 and his MSc in computational mathematics in 2016 from the University of Derby, where he received an award for his research in capacitated arc routing algorithms. Craig received his PhD in 2020 while working on the ALICE detector on the Large Hadron Collider at CERN in Geneva. Craig's work on adversarial threshold semi-bandits was also nominated for CERN Best Student Research Award. Craig is now a researcher fellow in the School of Computing and Mathematical Sciences at the University of Leicester. Craig has published works in reinforcement learning, digital twins, and multi-arm bandits. Craig's current research interests include online learning, digital twins, and scientific machine learning. So, Craig, here's is your stage, so you can just start.
Thank you, Kyle. So my name's Craig, and I am part of a team of about 30 researchers on a wider AI for Net Zero project called Self-Learning Digital Twins for Sustainable Land Management. My talk today is going to be a specific part of that project called Physics-Informed Graph Neural Networks. And the main point of this project is because the agricultural area in the Fens in the East Anglia produces about 37% of England's vegetables, and over 70% of that peatland is showing on the ground degradation, and almost a quarter of our deep peat area is cultivated, including almost 60% of this lowland fen peat. And because the peat is being exposed to the atmosphere, the oxygen in the air is combining with the carbon in the soil, and we are having significant levels of carbon dioxide emissions because of this use of this peatland area. A secondary part of this project is also the cause of methane emissions from ruminant farming, which involves cattle, beef cattle, dairy, and sheep. So a brief agenda for my part of this project today is a description of what the challenge is, how we're able to combine the data that we can collect into input and output variables for training, a graph adjacency matrix that describes the relationship between the input variables, how we can train a machine learning model to make predictions, what type of architecture that we're using, what the model is learning, and then how we can interrogate and use the outputs from the model afterwards. So a big part of this problem is because of the greenhouse gas emissions from the use of peatland agricultural farming practices stems from the complex dynamics of the interconnected relationships in the variables that we can take measurements on. The digital twin part of this project is a way of using what-if scenarios to inform farmers and policymakers into making informed decisions that can change the future state of the physical system itself. One aspect of the current technology that we use in this project is called the JOULES simulator, the Joint UK Land Environment Simulator. This is an idealized deterministic model driven by a system of partial differential equations that takes in past climate conditions, the soil characteristics, the farming practices that we can give as an input, and then produces a set of outputs that we can then model greenhouse gas emissions on. Along with that, eddy covariance flux towers are located on site in the field, taking measurements of the environmental conditions in situ, and we can also use those to reinforce the predictions that our model is then making. So a quick whistle-stop tour of what a digital twin is. Essentially, it's a digital replica of a physical system. And a user can give a digital twin a set of input variables, such as climate conditions, soil characteristics, and a particular crop. And then we can make predictions on what the greenhouse gas emissions and how much crop yield that crop can then produce based on those input variables. An easy way to describe what this system is modeling is a regression type problem where we're trying to find a relationship or a mapping between the set of input variables that we give to the model and the predicted outputs that it gives out at the end. The graph part of this model takes in the correlation between the input relationships that we are then giving to the model. For example, the pressure that a particular area is experiencing is related to the amount of precipitation that it's received, which is in turn influencing how much soil moisture that particular area has. And these variables are then contributing towards the output greenhouse gas emission that we're trying to monitor. In our model, we have a set of inputs of precipitation, pressure, relative humidity, surface net radiation, which is essentially how much sunshine the area is receiving, surface temperature, a crop sowing date, the shortwave downward radiation, which is another way of measuring photosynthesis for a crop, and a particular crop type. The outputs that we're predicting are the amount of plant respiration for that particular crop, the soil respiration, gross primary productivity, and the crop yield associated again with the same crop that's that input. So our training data is essentially a big table of numbers. Each row in this table represents one sample of data. We have all the input variables in the red box as shown, and the associated output variables that correspond with those previous inputs. We train our model to predict these outputs, and then we can interrogate new inputs and see what those outputs are based on the training of that model. The correlation matrix computed between each input variable is integrated into this model to ensure that the relationships between inputs is also reflected on how they contribute to the outputs at the end. We train the model in a supervised learning regime where we already know what the expected outputs are for a particular input. We train the weights of a graph neural network to give outputs that are as close to the expected outputs as possible, and then we try to minimize the difference known as the training loss for this model. The type of architecture that we're using is based on TensorFlow and Keras, and we're using the adjacency matrix for each batch of training data that we optimize on every training epoch. And then the final layer of the model is a dense, fully connected layer with the number of outputs corresponding to each output target value. The physics-informed part of this model is integrated into the loss function of the training process. One aspect of the gross primary productivity, which is one of the predicted outputs, is that it can never be a negative value. The same for the plant respiration. We will never physically measure a negative value for this variable. When we make a prediction from the model, we penalize any value that does go negative to constrain the model to make realistic predictions based on the physics understanding that we already have. That was our introduction to making this model physics informed. We've then upgraded the model to include more complex relationships, which I will discuss in a few slides down. But I also want to make a point of the model is learning that certain input variables are more important than others. For example, temperature in this particular iteration of the model has a significant importance on how accurate the outputs are. Pressure is also another important variable in this particular model. When we include the solar downward radiation variable, that bolsters not only the temperature, but also the net radiation of the inputs that we're receiving. And this is making it a more important feature for the types of predictions that we're getting out. So on screen are the outputs for our training data that was held back. So this is essentially a test data set, and we've quantified the error, which is relatively good. A point to note on the predictions for the crop yield in the dual simulator that we're using as training data, the crop yield value is a specific value on one particular date of each year. In order to train our model, in order to make predictions on a daily basis, we then convert that same one value for every day within that same year, and that constitutes the entire training data set for the crop yield itself. So this is why we're seeing these long lines of prediction values that are different for the same actual crop yield. To go back to my point about the physics-informed loss function, we also incorporate the relationship between gross primary productivity and global solar radiation based on the formula that we can see on the screen. Because we have data for net solar radiation as opposed to global radiation, we inspect what the relationship is using that variable instead, and those can be seen on the left-hand side of the screen, which are the in this particular case, it's the black lines, which are gross primary productivity, and the light red lines are the same values, but using this particular formula. And there's a relatively close correlation most of the time, maybe with some sort of offset. So what we're using is this relationship to ensure that the gross primary productivity that's predicted from our model adheres to this formula. When we interrogate the model, it's a case of performing inference on giving it a set of inputs and then seeing what the predicted values are based on those inputs. So we can interrogate different types of crops, different weather conditions, different soil characteristics, and then see what the predicted net ecosystem carbon dioxide exchange is for those sets of inputs. So in this particular example, we've taken a year of 2019 because we've got actual data to then quantify some sort of error against. And we give it the weather data that's taken from the Met Office CHESS datasets. And we filter the year for this particular table of data. We give it a particular location using the longitude and latitude values. And then we give those inputs to the model and then make a prediction for those on plant respiration, soil respiration, and gross primary productivity. And all those three combine to give us a net ecosystem carbon dioxide exchange for those inputs. I will make a point. This is a key point for the purpose of this digital twin. The user can then decide which crop best fits their land management practices based on the carbon dioxide emission profile that they're wanting to follow. If they have some sort of incentive, or if they're constrained by the amount of emissions that they can make, they can then make informed decisions on which crops they should plant based on the weather conditions that they expect to see in the following years. Now, when we give this data to real flux tower measurements that are taken in the field, we do have some discrepancy because the joules simulator that we trained the model on is an idealized system. When we give it real world data, there is inherently going to be some sort of gap between our predictions and what we're actually seeing. And this just gives a visual representation of the very good capability of the surrogate model, or the graph neural network model, to predict the joule simulator, but there's still a gap between what we're observing from flux towers. Now, just to finish off, our method for integrating the measurements that we're seeing in the real world, we can take an average over many different flux tower sites of a particular crop to get a crop profile for the net ecosystem CO2 exchange of a particular crop for many different locations, take an average of that, and then use that as a trend baseline to then input into our graph neural network to make predictions on a daily basis. This is then being used to make what if scenarios on the future climate scenarios given by the Met Office, different types of crops, different locations, and then different soil characteristics and soil moisture contents as well. So a quick recap, we talked about the challenging aspects of this problem, with it being a multi-variable type of analysis where each variable is interconnected with each other. We've been able to isolate some input and output variables for training, the type of model that we've used for that training, what the model is learning, the outputs that model is then giving, and then how we can then use the model to interrogate different types of scenarios and quantify how close those represent the real world at the end. So that concludes my talk for today. I think there is some time for questions now. Thank you for listening.
Thank you. Thank you so much, Craig, for that insightful presentation. Now we will move to our question and answer session. So please feel free to submit any questions and answers in the chat box, and then we will begin with the questions.
Great. Great. Thank you, Craig, for your presentation. That was really impressive. If you would mind, Goyal, if there is no question, can I ask some question? I have some.
Yes, sure.
Okay. So before that, I'm Amin from University of Saudi, co-chairing of this session. I have some question about your work. That was really impressive. First of all, haven't you considered the financial parameter in your model? Yeah.
Sorry, say that again, please.
I mean the financial parameter, like cost, like that doesn't.
The economic aspects has been in discussion, but it's not a focus for this particular project.
I see.
But
As well.
I can see the importance, particularly if we pursued further the analysis of crop yield. That's a proxy for the economics of what the farmer is seeing. But yeah, it's mostly about the emissions itself.
Yeah, that's my second question. What about the social factor, like job creation or decreation? I mean, because you mentioned farmers or farmer concern, so do you have plan to concern these things, some social aspects?
We do have a different project stream that's taking into account the social impact of this sort of work, not necessarily in terms of how it would influence people's employment, but the confidence that it gives to people in the uptake of using these sorts of technologies, particularly in an area where there is some use of technology. So a lot of farmers are technically quite savvy, but these sorts of techniques are still relatively new, and building interest in using these is inherent. It's expected that it's going to take some time, but we have to start somewhere.
Yeah, great. Is there any other question?
Yeah, Craig, I would like, as you mentioned regarding the adjacency matrix. So how means what the parameters or how did you form in your problem the adjacency matrix? I was interested in having a look or brief regarding that.
Well, we've got a training data set that's taken from the ChessMet data set, which is the measurements of all the environmental conditions in the area of interest between 2006 and currently it's only up until 2019.
Okay.
A new set of data is imminent, but hasn't been released yet. What we've then taken is each batch of training data that we use in the training step. We compute the adjacency of that batch of data against each other. So the relationships between the variables for each input has a weighting on how much that contributes to the output. So if one input increases by a certain amount and it has an influence on another input, then that will have an increased contribution towards the prediction.
Okay. Thank you, Greg. And I guess you also mentioned regarding the error quantification or error minimization. So how do you achieve that, or how much percent minimization did you achieve?
At the moment, we are at about 97% accuracy for the model on joules. However, joules doesn't always reflect what we're seeing literally in the field, and that's at about 75 to 77%. So there's a build-up of error as we add more complexity to the model.
Okay, thank you, Greg.
Thank you. If we have, okay, there is question.
Yeah. We have some questions, I think. Yeah. So, so Perez is asking that, do you have any insights on how you can identify the modeling discrepancies induced by the Joule simulator when compared to real data sets? Also, any missing components in the PDE model?
I can answer that question with one word, and that word would be no. But it is a piece of research that is being undertaken as we speak. Validation of joules against actual flux style measurements is a piece of work that's currently underway. And yes, I'm looking forward to seeing the outcome of that as well. So not yet, but hopefully sometime soon.
Okay. Thank you. Thank you for the wonderful presentation and wonderful answers. So I guess we don't have any more questions, so we can move to our next speaker. Yeah. So our next speaker is Andrei Dobrisan. So Andrei is a research fellow at the University of Birmingham, studying the effects of climate change on power generating infrastructure as a part of the VPP World project. He joined the project from Cambridge, where his research focused on mitigating risk associated with natural hazards, specifically analyzing the suitability of steel piles as tsunami defenses in Japan, as well as investigating the behavior of liquefiable soil during seismic events. So, Andrew, welcome. Now you can begin with your presentation.
Thank you, Goyal, for the introduction. Today I'm going to talk about how we go about monitoring the resilience of wind farms against a changing, more aggressive environment, and how the structure and the soil together, working together, can resist increased loading. So to start off with, we need to understand what sort of loads we have on a wind turbine. And these are your usual suspects. This is wave loading, an offshore wind turbine, a wave loading, as well as wind turbulence. And this graph over here, shows the sort of where we expect frequency-wise these loads to come in. So at the design stage, a wind turbine has a few options as to where to be designed. And a further mention would be these two intervals here of a 1 omega and 3 omega. These refer to the first and third frequencies of the turbine rotor, which of course we don't want the structure to be in resonance with. So one option would be to design the turbine to have quite a low natural frequency, but that would mean quite large rotations way above what we have to allow for a good mechanical operation. The other options would be to build a very stiff turbine, but that can be prohibitive from a cost perspective. And so we have this Goldilocks band between the first and third modes of the rotor. And that is generally where we build wind turbines in offshore wind farms. Now, the issue is that even though we can define what the frequency of the structure is, it will work together with the soil to resist the loads. And we're talking about hundreds of millions of cycles across decades, which, because the soil is a non-linear material, will lead to softening, which might mean that the wind turbine slowly shifts towards the first natural frequency of the rotor, which can cause issues with electricity productions at best and failure at worst. So we need to be able to quantify where the natural frequencies or where the frequencies of the systems are, and to account for the soil component of these and for cyclic degradation. Now, to better understand how in geotech we quantify this interaction between the soil and the pile, I need to introduce soil springs. So because the soil is such a nonlinear material, we think about it as interacting with the piled foundation of the wind turbine at each level, at each depth, with a nonlinear spring. And here on the right are some of the expressions we expect these springs to hold. And just to note here, when we go from 1 to 4, we mean increasing depth. And sort of intuitively, at increasing depth, the soil is it has more constraint, which means it's not as free to move. So we expect something with a larger stiffness and a larger ultimate strength. Now, the curves you see here, along with some of the others done in API and DMV, are the sort of way we design for the interaction between the soil and the pile at the moment. And these are based on very important papers from the 70s by Rees et al., who derived these empirical equations from data that they gathered on small, like 0.1 of a meter diameter flexible piles. Now, those piles are a bit different than the wind turbine ones. So we need to take extra care in how we use these formulae when we assess the frequency of our soil turbine system. And as a further component, we also need to think about cyclic degradation, something that is not explicitly accounted for in these methodologies. So just as a quick sum up, the way we define soil structure interaction is through these things called PY curves, essentially nonlinear springs acting at each depth on the turbine's monopile foundation. It dictates the natural frequency, obviously. These different spring constants will lead to different frequencies. The lifespan, because we need to take into account fatigue accumulations, and they're very important in determining the suitability of the system to produce electricity. Unfortunately, these springs are unique to each turbine. Since soil is such an inherently nonlinear material, we depend on profile, on the installation process, aging, etc. But if we would manage to quantify this PY in the field, it would be tremendously helpful, as it can be used as an input to an AI system, which, based on the characteristics of the springs, can decide how well the turbines, the wind farms are performing, potentially down to individual turbines. Now, the reason why there's actually relatively few experimental data on this topic is because it's a difficult problem to solve. Actually going below surface and accurately measuring the pressure between the soil and the steel body of the foundation is difficult, and so is measuring deflections below ground. Which means that the only way to quantify these measures is by measuring other properties on the pile, on the turbine, such as the strain, which translates to an elastic constant to moment, as well as through inclination of rotation of the body. And then we use the fact that all of the properties, pressure, shear, moment, inclination, and deflection, are actually part of one big derivation chain with what we want at the ends. And so, because we only have sparse data usually on structures, we only put our instruments at different specific location rather than continuously on the structure. It means we need to fit some sort of continuous function to our data and then integrate up to get deflection, differentiate down to get pressure. And so just sort of to show you what this means and how this translates to practice, I'm going to show you a bit of experimental data that we have. Don't worry about the tsunami wave there. It is because this type of monopiles are used in different applications, such as tsunami defenses. And so we have some data sets from these, but they translate equally well to turbine applications, since we are talking about the same sort of piles and same sort of pile foundation. This is sort of the experimental setup. And now I'm going to move into how we're going to present the data from this. So what we have here is the different graphs representing the different properties at one moment. So we are representing here the moment at which we loaded the pile at 2.4 meters above ground with a force of 1,000 kilonewtons, about one meganewton. And we can see here that represented in the shear force value. We can measure, as I mentioned, deflection, but only above ground, since measurement underneath ground is very difficult and error-prone. However, we have plenty of instrumentation to measure inclination as well as moment. So with this data, we want to define the continuous profiles of deflection and pressure, which we can then use to inform our PY springs. And so the first thing to think about is to fit a polynomial, and that's what's done in practice. Let's say a sixth order polynomial and moment. That looks pretty good, and we integrate that up to deflection, and then we differentiate that down to net pressure. Things look relatively well behaved. However, if we think about the physical properties of the system, we'll start seeing what the issues are with these fits. So first of all, I think intuitively, at the depth below ground at which the pile does not move, given that it's connected to a soil spring, that should be the same depth at which we should see no pressure applied from the soil on the pile. And in this case, the predictions are a bit different. One's at 4 meters depth and the other one's between 5 and 6 meters. That is an issue, but actually the more significant issue is the prediction that with increasing depth, actually the displacement increases. Now, if you recall at the beginning, I mentioned that as we go lower and lower, we expect the soil strength to increase and the soil stiffness, which would mean that this should translate to a big increase in soil pressure, not having it drop close to zero. Okay, so we can say, oh, maybe this is because we haven't fitted a big enough polynomial order. So let's do a 7th order. Okay, we see a big increase in pressure. However, the top of the polo doesn't look good anymore. Maybe we can then argue that moment is the issue. We can actually fit our rotation data. If we try to do that, things get completely wacky for differentiation. So when you're trying to do net pressure, the graphs are not legible. However, interestingly, in deflection, things seem a bit more sane with significantly less deflection towards the bottom of the pile. And you can see sort of where the problem with this methodology is. Since there is no clear way to pick what fit to use, people have resorted to try through trial and error and finding what the best fit is that works with their geotechnical understanding of the problem. So if we want to automate this, it is definitely we need to find a robust way to solve this issue and to fit this data. And another issue is that even though we have data for different properties across the steel pile, unfortunately, we can only fit one property of a time and then use the rest of the data just to compare and to assess the fitness of our polynomials. And so we developed this methodology to kind of address these issues. And the way it works is that we are searching for all polynomials. We devise a code that searches for all polynomials of a certain order that fit all of the data provided within certain error range. And then we provide these polynomials to the user, and these can be millions of polynomials which all fit the data right, so then we can do reasonable statistics to obtain credible intervals for the properties we are looking for. And just to sort of show you how this method, which we call multi-fit, works in practice, we can see the results it gives for a sixth order moment plot, so 18 deflection, sixth order polynomial fits in moment, and we can see that the results are much better. First of all, our credible intervals both in deflection and pressure suggest the crossover point is between 5 and 6 meters, which is something we want to see, and all of our data is taken into account and is well matched by the fits. However, we still, even though we have a very good result at depth in deflection, which shows that indeed the pile did not move significantly at high depths due to confinement, which makes sense. The soil pressure plot shows that does not have enough information to make a decision. And this is where a second strength of the method comes into place, which is a sort of human in the loop bit where we can assess these fits and realize that the deflection data gives us enough confidence to tell the method to search at depth for only negative pressures, i.e. ones that make sense for a spring. And that refines the analysis further. And we managed by doing 2 simple runs to completely represent the results from our data and obtain credible intervals, which across the board make geotechnical and physical sense. So that's very encouraging. But keep in mind that all of these plots happen at the instance in which the simulated force is 1 meganewton. In these experiments, we have a varying force, which means we can draw these graphs for consecutive loading, and that means we can assess what our PY plots actually look like. So we can see here, for example, at 2 meters depth, the comparison between our data set, the empirical relations from Rees, that paper in the 70s, as well as the API standard. And while the API standard is quite far off, it's impressive to see that this empirical correlations done by Rees in the 70s still matches really well with data on these big, much stiffer piles that are used in wind turbine installation. However, as we go lower and lower with increasing depth, we see that both methodologies, theoretical methodologies, significantly overestimate the stiffness of the PY curve, so the stiffness of the soil. which actually means that when we design these wind turbines, because the soil is not as stiff as we assume it to be, it probably is actually closer to that 1 omega range, so the rotor frequency, than we expect it to be, which means that we might actually have less cycles to work with until fatigue issues kick in. And actually, what's very interesting is that these standards that I'm referring to here make a bit of a reference to that, in the sense that they provide a huge range for initial stiffness. Okay, refers to the initial stiffness based on a property of soil that's difficult to get to that level of accuracy. So that means that within 6 degrees of measuring the internal friction of the soil particles, you have more than a doubling of the presumed stiffness, which shows that in a way, the current methodology is aware of the inherent issues in predicted stiffness and indicates that we need to think about measuring PY as well as possible empirically, not just to continuously assess, but potentially to continuously assess the state of the turbines, but potentially also to draw up more accurate ways to predict it. And because, like for now, I've showed you a multi-fit results from through experimental data, we have also devised a test that's actually quite difficult for it to do on a theoretical basis. So we can have a measure of assessing how well the fits do compared to the real scenario. And here are some of the results for moment, shear, and net pressure. And those of you that might have had experience with polynomial fitting might know that as you increase the order, you tend to get high oscillations, which make your fitting less and less accurate. However, because multi-fit amalgamates the results from so many different polynomials, it's actually quite resistive to this and manages to not just increase accuracy with order, but then plateau in a way that makes you more confident that the results you're looking at are the best you can get from the data you have. Okay? And so to sort of sum up the challenges that we are still facing with this new methodology, unfortunately, the computation time increases exponentially with polynomial order. This is commonly known as the curse of dimensionality, because it adds another layer of complexity every time you ask it to predict for another order in your problem, another degree of freedom in your problem. However, we've adapted a new mathematical paradigm in the code, and that has managed to actually significantly decrease the computation for low to medium-sized problems. So, for example, here we have 9 degrees of freedom, so 9 dimensions, and we went from spending about 3 days on a supercomputer to about 1 hour and a half on this laptop, which is very encouraging, and it kind of helps us sort of be on our way to trying to make multi-fit as close as possible to a real-time monitoring tool. And the reason for that is because we would like to get, as we get from wind turbines, their real-time data from the strain gauges or in the inclinometers that can be fitted to these structures, we can quickly compute these PY curves, and the VPP Word AI, which is supposed to be a routine to kind of predict where electricity generation issues might occur, and then spin up backup options, can make fairer and more informed assessment on whether wind farms can withstand an upcoming large storm or how they are doing in terms of fatigue, and then can account for that such that power generation is not interrupted. Okay, that's my presentation. Thank you very much. And yes, if there are any questions.
Yeah. Thank you, Andrei, for your wonderful presentation. Now we will be moving to the question and answer sessions. So, Amin, do you have any questions? Amin, can you just unmute yourself?
Yeah, sorry. Thank you for presentation, Andrei, and that was really impressive. I have a question about your last slide about the new method for decreasing huge decreases in your computational time.
Yes.
Could you a bit explain about it, how you could catch these reduction?
Yes, of course. So basically, when you're trying to find these polynomials that fit your problem, it translates to basically there's this, in n dimensions, a shape called the polytope, which you can think of as a shape with straight edges. And we're trying to find to sample within it uniformly. And before, we would need to split this polynomial into, think about in 3D a tetrahedron or a triangle, so basic shapes to be able to do sampling effectively. Because trying to just start with a point and then try to, hit and run, like try to do sampling starting from one point and branching out, even though it was faster, it wasn't that accurate. And in this sort of field, in this mathematical field of convex shapes and convex, now it's in the field of convex optimization, there is a relatively new routine which involves moving these polynomial edges quite far away to infinity and then doing what's called a log sampling. And that seems to help dramatically decrease our computation time, our time to find these polynomials without significantly influencing the accuracy.
And how about the error, after this modification?
So that's why for now we're restricting it to medium and small, to medium-sized problems, because as I said, with the curse of dimensionality, the bigger the space is, the harder it is, especially if you start from one point and then you're trying to blindly go around and doing it by trial and error. But this method, up to 9th degrees, which sort of give you already a reasonable value, it is next to indistinguishable with the one that does it exactly, but slowly. So it does it quite well, but indeed there are challenges at 10th order, 11th order, and beyond, because you need to leave it significantly more time to do sampling to reach the harder to reach regions of the space.
I see. Thank you.
Nice.
Thank you. Thank you, Andrei. As you mentioned that you will be directly incorporating this to increase the resilience of the wind farms or the wind power plants. So can you just give us again little bit brief how you can how you will be directly incorporating into the project, as you mentioned, the VP award for increasing the resilience?
Yes. So generally speaking, companies and power utility networks have some sort of instrumentation on the wind turbines to assess how they are doing. So that would involve strain gauges, inclinometers, the sort of inputs that we can use into multi-feet. And the idea is that by multi-feet ingests these inputs from different wind turbines, different wind farms, around the UK, and spits out this PY, like these nonlinear springs. And what we can feed into the algorithm is basically where we are currently, or potentially the whole history we have on the PY path. And based on that, we can decide whether we fatigued too much. Like the AI, based on experimental data, can decide this is too much fatigue, this is not, a good turbine to rely on when the storm comes, which will push it even more. Or potentially, if we have a future storm condition, based on past data, we can estimate how big of an impact it will have, how much it will tense the springs. And if the AI says this is too much, based on training data, it can say, oh, this field will not be okay, shouldn't be operated during the storm condition that's upcoming, which means I need to spin up more VPPs, more storage capacity ahead of time to fill that up so I have it during the stormy conditions.
Okay. Thank you. Yeah. I think we don't have any more questions. So, can we just move ahead, or do you have any questions?
If there is time, I have another question about the wind farms, about the wind turbines. So what about this wind turbine that, the operational parameter from this wind turbine, where is it came from, and it is suitable, which standard you follow, or which class you follow?
So what we would need, I've been in discussion with contacts at companies that sort of manage this sort of stuff. They install wind turbines, and they have a significant amount of data on their operation, especially historical data. And the way you monitor them is through instrumentation, as far as I'm aware, like strain gauges, inclinometers. And the idea is to use the past data, run the multi-fit analysis, and show sort of what has happened historically in terms of PY degradation.
Mm-hmm.
And then, because we know the data is out there and it is being monitored in real life, we use the past data as much as possible and knowing what has happened to train the AI in terms of what's preferable, what constitutes, like a danger. And then we apply that to current data as it is being pushed forward in time.
Okay, thank you so much.
Thank you.
Okay. Thank you to all the speakers for sharing their expertise today, and thank you all for joining us. So we are excited to announce our next session, which will be taking place on Tuesday, that is 19th November at 2 p.m. So in this session, we will have Professor Bayua Lee from Loughborough University, who will be presenting on AI and digital twin for sustainable agriculture. So this will be a great presentation from an expert who is from the AI and sustainability field. So please join us. Additionally, on behalf of the UKRI AI for Net Zero program, we would like to highlight a conference which is taking place from 16 to 19 December 2024 at the University of Exeter. So this conference will bring together the leading experts and high-profile speakers to discuss how AI can drive meaningful progress towards achieving net zero. Registrations are still open, and you can find more information through the link which is posted in the comment box. So everybody can have a look and register and join us in the AI for Net Zero conference at Exeter. Thank you all.